here, so I'll continue with the talk. So the talk is on the probabilistic models for safety assessment of autonomous vehicles. And this is collaborative work with several colleagues from the Intel labs in Germany. Intel launched just before COVID, they call it Intel Collaborative Research Institute. And CT were working in this institute together with 5 German universities from, and the point was indeed to look at the difficulties, problems with the safety assessment of autonomous vehicles. So this talk is going to give you a probably slightly different perspective using methods which have been quite successful and are still quite popular in safety assessment of traditional systems, not related to systems where some of the components rely on machine learning or artificial intelligence. So I'm just giving a bit of a context. So the talk is quite ambitious. Probably I'll have to cut some of the details because otherwise you probably are going to get really bored to hear me speak. But nevertheless, motivation, why we do it. And then I'll outline the approach, which is not to concentrate on the so-called functional safety, where the problems are seen in the fact that some of the components fail, and therefore you look at the consequences at the system level. Instead, we're saying, even if the system works perfectly well, it is really the environment which may create hazards, and these hazards in some cases may escalate to failures. So there are, in fact, 2 separate studies that I'll try to cover in the talk. One is to give you the basic model, which spells out the approach using stochastic activity networks formalism. And this work was presented as there is a publication. So if somebody suddenly gets excited and wants to follow it up, you can. There is a link included in the presentation to the publication, or you can contact me. I'm happy to share the text of the paper. And the second one, which is still work in progress, we are yet to finalize it and complete it, and possibly there will be a further publication, is on a more detailed model where when we are taking into account the fact that on the roads you have intersections, and then you have periods of or intervals on the roads between these intersections, and taking into account this topology of the roads gives you additional details. And we tried in the second study to take this into account, use the proprietary data set, which provides which is a rich data set, which allowed us to estimate quite a few of the parameters used in, you'll see, quite a complex model, and to do something useful with it. But the key, and this is a common part in both, when it comes to parameters which affect directly safety, this is the quality of the perception system, whether the object obstacle on the road is recognized on time and correctly, or the quality of the so-called safety monitors, which are the solutions which are included in the AVs to deal with any eventualities and thus try to prevent accidents. So this is these parameters are very, very difficult to estimate. And in our work, we took the view that rather than looking for data sets, which even if you find them, they will be very, very limited to specific set of circumstances. We said, why don't we undertake so-called sensitivity analysis and say, what are the how these different parameters which capture the quality of the perception system, there are different failure modes. I'm going to discuss them all. The weaknesses of the safety monitors, how these different problems can affect the system of the AV as a system at the system level. So this is probably the most significant part of this work. Motivation. Safety assessment is a challenging task. There are a lot of conferences, a lot of publications, and everybody agrees that we are very far from having a comprehensive solution to the problem how to assess the safety of the cars. There are international standards. Some of you who are interested in this area may have come across. I only listed two of them. The safety of intended functionality, which is a relatively new standard, and the more mature by now ISO 26262, which is seen by many as the Bible in automotive industry. But this standard is not really dealing with the AVs per se. It is rather looking at the assessment of individual components, the so-called ECU components in the cars. And of course, there are other guidelines. In Germany, they are quite keen to accumulate in guidelines the current understanding in the area. Similarly, in the US, of course, in the UK, we have our own set of guidelines. Also, there are alternative approaches when it comes to safety. A couple of years ago, probably more than a couple of years ago, a team from the RAND Corporation came up with quite a clear model, and they essentially, this is now known among the community as driving to safety. So essentially, the point is how many miles autonomous vehicle need to have driven successfully in order for us to conclude that this particular AV, or maybe the AV as artifacts, are sufficiently safe to be licensed for use on the public roads. And my colleagues have published quite a number of papers where they scrutinized the original publication by the team from the RAND Corporation and came up with the so-called conservative Bayesian assessment, where they try to put to develop an assessment framework which will be based on the amount of miles or kilometers driven without any failure, but do it in a conservative way. So whatever the uncertainty about our knowledge and so on, the conclusions that you get using these conservative methods are unlikely to surprise you in the sense of coming up with some conservative, over-optimistic predictions. And the problem that is addressed in this talk is summarized in this at the bottom, the wording in red. How can we demonstrate that the AV is safe enough to receive certification to participate in a regular traffic? And a bit of a context. Road hazards. What are the road hazards? The road hazards are situation on the road which may or may not escalate to accident. And these are beyond our control. This is really the environment in which the car is operating. But the key here to recognize, and this is what we exploit systematically in our approach, is that if there is a hazard, the chances of having an accident eventually, this is the safety-related event, are likely to be visibly higher than if you're driving in the middle of nowhere, there is nobody on the road, and therefore, even if your car fails in a very serious way, the chances of having an accident in the sense of hitting somebody is zero because there is nobody around. So this is the law. Hazards are what causes eventually the accidents. In the absence of hazards, the likelihood of accident is significantly lower. This is what we take into account. And the second element of this work is that we look at what makes the AV different from the other safety critical system. And here the elephant in the room is obviously the perception system, the perception system based on machine learning. If your perception overlooks obstacle on the road or classifies it incorrectly, not surprisingly, the consequences of this failure are going to be, or maybe, very dramatic. The second problem, and by the way, if the perception system fails to recognize a hazard, for instance, an obstacle on the road, this is not necessarily forever. Just missing it and it stays unnoticed forever. This may be for a very short period of time, a second, maybe a couple of seconds, and eventually the perception system may recover and seize the hazard, assess it correctly. So we're trying to capture this in our models and see what are the consequences of parameters which represents the details of what is happening on the road. And the second aspect, which is somewhat touched upon, are the so-called false alarms. Perception system says there is a hazard on the road. This is strictly, one may say, not a safety-related problem. Because, okay, false alarm, you stop the car unnecessarily. How is this going to affect safety? This is strictly not true, because if you're driving on the road and there is another car behind you, and your AV suddenly, without any obvious reason, stops because the perception system decided that there was something dangerous on the road, the guy behind may not realize that you're having a false alarm and they may hit you big time. So this may lead again to an accident. So we're looking at this aspect too. Okay, again, to go a bit further, so hazards, how do we model these hazards? So luckily, in the standards, there is a very specific recommendation how this can be done. ISO 26262 is quite specific and says hazard occurs at random and lasts randomly long. So this gives us enough information to use the recommendation by the standard and put it in the probabilistic model that I'm going to show you in a minute. So we essentially use a stochastic state machine in which the state of hazard on the road is represented by a specific state, and then how long the model will stay in this particular state is a random variable, which again, the parameters of the random variable can be estimated using the available data, publicly or proprietary data. But this is conceptually very clear. We have a state, and how long we stay, the model stays in this state is governed by a probabilistic parameter. And apart from the hazard, now we say, okay, provided the hazard exists, the two situations which are effectively failure modes of the vehicle are the failures of the perception system, the two that I already outlined, overlooking an existing real hazard on the road, possibly for a short period of time. This is one failure mode. And the second is the false alarms. Perception generates fake warnings that there is a hazard on the road. And of course, the second is what about the limitations of safety monitors? Everybody says, oh, the safety monitors have to be very reliable. The question is, how reliable is good enough? Can we study by sensitivity analysis what are the implications of having probability of failure of the safety monitor 10 to the -6, which seems quite a small number? Is it good enough? So these are the problems that we try to address. So the basic model, I think this is more or less what I already said. So what we take into account, failure perception system of two kinds, and then the failures of safety monitors and false alarms. The paper is published. If somebody is interested, please go and read it. You may find it interesting. If not, at least you'll see what we have done. And now the model. After so many words explaining what the model does, this is what the model looks like. We have several states. One is the okay. There is no hazard on the road, and everything in the AV works correctly. Hazards occur with some intensity. They are random, but nevertheless, there is a stochastic process which you can study in order to see how frequently and what are the characteristics of the times, the distribution of times between the hazards. And once the hazard is occurring, the AV may recognize this hazard immediately and correctly. So this will be handled by this possibility. We end up in a state called correctly perceived hazard, or alternatively, the complementary to event is that the hazard will be overlooked. So the car will continue to drive, to be driven, without recognizing that there is a road hazard. And then the thing that I pointed out is that this may be a temporary. For a very short period of time, we may have a problem with the perception system. So again, after a short period of time, either the hazard will disappear, or it will be eventually recognized correctly, and we end up in a state which is similar to this correctly recognized, but not quite the same because some time has been lost. And therefore, the situation may be quite different from recognizing the hazard on time. And finally, to finish with this branch, we have a state, the so-called in terms of these probabilistic models, absorbing state. This is the disaster. Accident occurs. If the accident occurs, the game is over. We're not interested to see what happens afterwards. And here, this branch captures the possibility of having false alarms. So again, from the OK, every now and then there will be a false alarm, which gets us to a completely different state. And again, from this state, a false alarm will have a possibility of having an accident. So again, here there is a possibility to go to the accident. If the hazard is recognized correctly, we may stay in this hazard for a certain period of time. And again, this period either finishes in an accident or the hazard goes away on its own. This is, after all, the hazards on the road, they occur all the time. And as drivers, we know that this is the case. So this is the model. So the four states are, or the states in these models are listed here. We have transitions between these states, and the formalism that is used to build this model is the so-called stochastic activity networks, which is a generalization of stochastic patterns, a popular formalism supported by a specific tool that was used to solve these models. And here we made simplifying assumptions just to make use of this is convenience. It doesn't have to be. We don't need to make exponential assumptions about the all time activity being exponentially distributed, but I'll show you how fitting the available data, they're not too far from exponential distribution is not too bad. But in a sense, we know that this is not real requirement. We can drop it, solve the model using Monte Carlo simulation, or rely on asymptotic solutions, which eliminate the type of the distribution. You really need to have 1-2 parameters maximum in order to get very accurate approximate solution. Okay. State and then absorbing state, I already mentioned it. Now, what are we interested in? With this model, we are interested to know the probability of having an accident within a period of time of fixed length. And so the length that we have chosen for this study is, first of all, what is the probability of having an accident within 100 hours of operation? 1,100 hours of operation, or 200. So the choice of these numbers is relatively arbitrary, but what we are saying is when exactly within the 100 hours we don't care. We're interested whether at the end of this 100 hours there has been an accident. In other words, the model entered the absorbing state accident or not. And similarly for the remaining. So this, in a sense, is telling you how the time to accident, increasing it, will affect the probability of having a safety-related event, which is the entering the absorbing state of accident. By the way, this intervals 100 up to 9,100 hours of driving. It's not calendar time, it is driving. If you drive it every a couple of hours a day, this may take very long time as in calendar times. But the data that we use is to parameterize the model, and I'll explain in a minute, is from data collected by a drone on German motorways. So the range was between 100 and 130 kilometers per hour. This is how many kilometers the car can drive per hour. So if you look at the 9,100 with this speed, this amounts to quite a significant number of miles. We're talking about almost 1 million kilometers. What is the probability of observing an accident within 1 million kilometers of driving? So case probability, the details, if somebody is interested, happy to take this offline and provide further details. Okay, so the model parameterization. So, with this model, we have quite a few things to parameterize. The rates, even though we assume the exponential distributions everywhere, there are still quite a few of them. So we need to have these parameters. Then we have case probabilities, which says either the hazard disappears or after the duration you end up in the accident state, and so on. So there are quite a few parameters. Some of these parameters can be estimated using the available data, and we use the two publicly available data sets. This is high D data set, is the data set which was collected by flying a drone on the motorway and collecting the cars, how the hazards were estimated. The colleagues from Intel, they use the so-called RSS. This is the responsibility sensitive safety, a concept put forward by Mobileye. Mobileye is one of the allegedly leaders in autonomous vehicles, an Israeli company acquired a few years ago by Intel themselves. And so RSS was applied on this traffic. And then whenever the rules of RSS is effectively a set of rules, wherever what means to drive safely, whenever the rules are compromised, then this analysis will flag this is a hazardous situation, and then we'll measure for how long this hazardous situation will last. So effectively, using this data set, we can quantify what is the distribution of the intervals between the hazardous situation, and then how long this hazardous situation will last. This is what we can get directly from the high D data set. LIFT data set is also publicly available. This is quite different, and it's really telling you what is a perception, object recognition. If you apply it to images coming from a camera driven on the autonomous cars, the image will be maybe overlooked for a while, and then eventually it will be found. So this whole point of this second data set is to allow us to see what is the duration of overlooking objects, if they exist, but the camera and the machine learning object recognition is not detecting them instantaneously. So we use this second data set as to help us with this case probabilities, this distribution. How long we spend in this state of not seeing the object on the rock. How I'm with the time? I should be wrapping up.
5 minutes.
Okay, so fine. I'll try to finish the first. By now, you should be clear what we have been doing, and then there are model parameters. So the ones that are estimable from the data set, I already explained how this is done. And for the remaining parameters, which are the transitions to the accident, we use sensitivity analysis. And the purpose of the sensitivity analysis, you saw, there are quite a few transitions to the accident to say which of these are important. Do we need to worry about all of them? Or maybe there are some which make a huge impact in terms of affecting the safety of the car, and some may be quite negligible. So this is what numbers, I don't expect you to follow, and therefore I'm not exactly what they are. But if somebody is interested, again, this is in the paper, spelled out, and so on. So let's look at some of the numbers. So we have a model, we did the parameterization, we do sensitivity analysis, which means that we pretend this parameter will have value so and so, then we change it to something else to see how the change of the parameter value affects the, and there are two groups. Initially we say if the recording the, assumption immediately and correctly, accident cannot occur. So we are chopping the second part. We are saying here, if we are here, this is practically set to 0. The only possibility for a real accident is to have them from somewhere here, from the lower branch. And let's see what's happening. And there are two groups. Then we relax the even if it is recognized correctly, there still may be a probability of accident, probably with a very small value. Okay, so this first case is telling us that missing, if we varying the probability of missing a hazard, the hazard occurs, we miss it, it impacts the safety quite visibly, but still, with this level of parameters, no probability of accident to 10 to the minus 4 or 5 10 to the minus 4, the safety after 9,000 hours of operation remains really modest. We're talking about 8% only. So here, the second parameter, this is interesting and potentially very useful. Machine learning is overlooking the hazard, but for a very short period of time. Based on the second data set, it was between 1 and 3 seconds. And it turned out that this very variation of between 1 and 3 seconds doesn't make much difference. Practically, the values which are assigned here, this is 1 to 3 milliseconds, the safety remains practically the same. So this is a quite practically important. So what's here? So here we had this second, if it is overlooked and eventually it is detected, how much the likelihood of accident from this delayed, detecting correctly the hazard but with some delay, how significantly it affects the safety. Again, it is visibly affecting it. The curves are quite different, but the overall, it's 4% over for 9,000 hours of operation. Again, quite a limited impact. And finally, if we allow for, this is the model of safety monitor. We say in the first three, we assume that if the hazard is recognized immediately upon occurrence, then accident cannot occur. Now we are saying, even if you do it instantaneously and correctly, we allow for a very small chance for an accident to occur. And look at these numbers, 10 to the minus 6 or 210 to the minus 6. With such a small probability, if we allow for the accident to occur, we are talking about practically accident with certainty. Compare this with the previous figures. The previous figures are here. They're practically very, very low. Now we see that this parameter is drastically affecting the safety of the car. So this is just to give you a flavor of what we have done with this study. Unfortunately, I don't have the time to finish the presentation. The presentation includes the second case study, but I'll probably skip it and maybe some other time, or will be other opportunities to do it. So to summarize, here we have, you see how many slides I prepared. To summarize, this is the model. The value of the model is that it allows you to do this sensitivity analysis and find out which problems affect safety significantly. And therefore, people may later say, if this is so critical, either I measure the parameter, the reliability of my safety monitor very accurately, but because I see even 10 to the -6 is not good enough, this will make my system practically unusable. I need to target the safety monitor with significantly better reliability. Or if some of the parameters, as we have seen, the overlooking for a very short period of time, the not recognizing the object on the road immediately, it's not a big deal. You can just ignore it because it doesn't make any visible impact on system safety. So I'll stop here. Hopefully it was clear what we have done. And if there are questions, I'll be quite pleased to try to answer them.
Thank you very much, Peter, for your very interesting presentation. And now we have time for question, online and offline. First one, Dr. Oleg Ilyashenko. Welcome.
Thank you, Peter, for your presentation. My question will be as follows. Did you consider different levels of automation of AV systems, or is it a black box? Automation is
okay, we didn't. Clearly, the implications here are probably the highest, full automation, but this was not really an issue for us. Even if you take an individual function, clearly the model is about the safety as a whole. Talking about individual function is probably not acceptable. So the honest answer is no. We didn't explicitly look at these 5 or 6 levels of automation, but implicitly we are talking about the highest, where you have a full automation.
Because I was thinking about ADIS, the Advanced Driver Automation System. It's about level 3. Yeah, I was thinking about that.
But the ADS level 3 is not really where the car is. So you have somebody supervising at least the driving and so on. Well, this thing obviously is we have a failure of the perception system, which eventually leads to something else, and the safety monitor cannot deal. So again, I don't want to fantasize here, but the implications are that implicitly we talked about the higher levels of automation.
Mm-hmm. And the second question is very short. What do you consider some specific implementation of AV? Or just a black box right now?
For us, it was important to have the concept spelled out in a model where the hazards, which is the environment, combined with the potential limitations, not necessarily failures, because perception, everybody knows that the perception is quite limited. 10 to the minus, what I said, 4 is unthinkable. You can't have a perception system with this level of reliability. They talk about 80% to 90% is the accuracy of object recognition. This is what is achievable. We say that even if you have several orders of magnitude better perception system, this is probably going to be a serious problem. And what was the second one?
The second one was whether do you consider any specific implementation of AV?
No, this is Intel. We are academic. We are free spirits. We just develop models and enjoy the observations. The implementation details, we are happy to delegate it to the people who want to make money. It's not our business. Sorry.
Mm-hmm. Yes, thank you. And one more question, Igor Klushnikov. Welcome.
Good afternoon. Thank you for a very interesting presentation. And my question is, you talked about hazard recognition. How many kind of hazard we use in your model? And which size of data set to deep learning was?
Okay. We don't, you probably realize that this model operates at a relatively high level of abstraction. And the beauty of it is that we didn't have to go and spell out these are the hazards that we want to take into account. The second part of my presentation would have answered to some extent your question, because in the second part, which I couldn't cover, we had different circumstances where we are again talking about the hazard. So in the second part, we consider at least 8 different hazards, and we allow for the likelihood of manifestations of these hazards to be different. Here, we simply don't know. We just say we lump everything in a single category. The hazard is there. But of course, we thought of hazards such as object recognition of the road, or the object not being properly recognized. But again, this was conscious decision made on purpose. And I don't think it's a limitation of the work, because if you have a list of hazards, whether there's 100, 200, and so on, this modeling framework can easily be expanded to deal with any number of specific hazards.
Thank you.
As a question, Artem Abakumov, welcome. Is on chat. On
the chat, let's see the chat here.
Yes, yes. On the slide 4, you have mentioned a short delay after hazard happens. Is there any possible ways to mitigate the delay?
Possibly, but based on our study, it turns out that if the overlooking the hazard is in this range between 1 second and 3 seconds, it really doesn't matter. Therefore, even if you can mitigate, this will be effort probably wasted, because it's not making any difference in terms of system safety. This is one of the most specific outcomes of this otherwise quite abstract modeling work.
Thank you.
Okay, and Artem Perepelitsyn, welcome for your question.
Okay, thank you for your really interesting report and presentation. So the question is, if it's possible to consider some maybe ecosystem of road infrastructure that provides additional information to add some extra information about the situation on the road, is it possible to add to this model such parameters and maybe information from another cars to improve the results and use an additional source of information for the model?
Conceptually, no problem. I've used the same sums for thousands and thousands of different entities. And your question points to something quite important, and with my PhD student, whom we are going to hear later this afternoon, we're looking at the cuffs, where the cuffs are communication between the vehicles, but also communication between the vehicle and this infrastructure, which is supposed to provide additional information for situational awareness and so on. So absolutely no problem. If you have specific needs or something very specific scenario, I'm more than happy to take this offline and see what can be done and how this model can be adapted to the specific need. But the short answer is no problem.
Okay, so the model allows such kind of scaling. Okay, thank you.
Thank you. Dear colleagues, we have not enough time. Just for me, for my question.
Okay.
A very short question. What about reasons of hazard? I mean failure equipment, problem with driver, cyber attacks on vehicle-to-vehicle communication, so on.
The hazards, what we call hazards in this work, is related to the environment and only to the environment. But of course, you are right. So the hazards are things which are happen in nature. We have no control. Of course, if we extend the hazards to be cyber related hazards, then we have to deal with. But the cyber related hazards will be not creating something artificial in the world unless some divine spirit can start putting objects on the road, and they will create this artificially created hazard. This will be really changing the behavior of the components. And the components, we take them that they have certain properties, reliability in this model, reliability of the perception system, reliability of the safety monitors. And of course, via cyber, these parameters can be changed to something completely unrecognizable. But this is, again, part of the framework. If they change as a result of cyber attacks, then the assessment will be very... And by the way, this is the essence of what my PhD, Arya Kosari, is going to report this afternoon.
I can say we can talk about two-level models, yes? And your presentation related to top level, yes?
Yes,
okay.
Yes.
Thank you. Any other questions? No? Thank you very much, Peter,
Okay.
for your presentation.
Thank you.
Okay, let's go ahead. And our next presentation.
With the title Artificial Intelligence and Cybersecurity, a Viable Partnership by Sokratis Katsikas. Sokratis Katsikas is director of Norwegian Center of Cybersecurity in Critical Sectors and professor with the Department of Information Security and Communication Technology, Norwegian University of Science and Technology, Norway. And he was also professor. He is also professor emeritus in the Department of Digital Systems of University of Piraeus in Greece. In 2019, he was awarded as a doctorate honoris causa from the Department of Production and Management Engineering of our Greek Demokritos University of Thaki. And last year, he was ranked 7th in the security professional category of IFSEC Global Influences in Security and Fire list. He is author and co-author more than 300 journals, papers, books, proceedings, and he, of course, chaired more than 800 conferences as TPC member. Of course, now he's chairing the steering committee of a SOREX conference, and he's editor-in-chief in the famous International Journal of Information Security of Stockholm.
Nico, thank you.
Professor, and one of our best friends in our life, Sokratis Katsikas.
Thank
We
you
are
very
very
much.
glad that you came from Norwegian special for us here to make in person this lecture.
Thank you very much, Nico, and to all the organizers. It's been a pleasure being with you, and thank you for the invitation. I hope next time the conference will be held in Ukraine.
Yes.
I'm sure about that. Yes, and I'm looking forward to it. Okay, before starting talking, let me just make a disclaimer. I'm not an AI expert. I don't pretend to be one, and I don't intend to be one. My work is in cybersecurity. But of course, these days, AI as a technology is permeating almost everything. So willy-nilly, we have to work together with AI. So please excuse any biases that I might have in favor of cybersecurity or against AI during the talk. Now, let me just make sure that I see what I'm doing. So the agenda for the talk, or the intended agenda, I'll just give you an introduction. Then we'll talk about AI for defensive cybersecurity, AI for offensive cybersecurity, cybersecurity of AI. As we will see, there are lots of problems that we face in these uses. So the natural question is, can we do anything about it, or do we just wait and then see what happens, and of course sustain the impact? And of course then a few takeaways. Before that, let me just give you a few information about where I come from. So NTNU is the Norwegian University of Science and Technology. It's the largest university in Norway. We have about 40,000 students, and it is a research university. So we have more than 400 PhD dissertations per year. There have been 4 Nobel Prizes awarded to professors in NTNU. Research labs, more than 100 spin-offs. We were talking about startups in the morning. I do agree with several of our colleagues' comments, but there are some that I disagree. But I will not comment on this too much. Otherwise, we will diverge from the talk. But I will give you some hints. Okay, the rest is about the size of the university. And of course, what is also important is that we are the university with the most, the highest research funding from the Research Council of Norway. Campuses in 3 cities, main one in Trondheim, and the other 2 are in Ålesund and Gjøvik, and I'm situated in the Gjøvik campus. The second affiliation, which is actually the same, I mean, I am a professor at NTNU, but I'm also the director of this Norwegian Center for Cybersecurity in Critical Sectors. SFI is the Norwegian acronym of Center for Research-Based Innovation. So this is a public-private partnership. It's one of the instruments of coming close with the industry for doing research, of course. So it's 18 partners. Some of them are research institutions, but the rest are industry partners coming from energy, manufacturing, the oil and gas industry, cybersecurity industry, the healthcare, the police, the process industry, the defense industry, and so on. This is an 8-year project. The budget is more than 20 million euros, and this is only for paying PhD students and postdoc students. The rest comes from the investment of the partners. And the funding, of course, has to be less than 50% from the Research Council. More than 50% comes from the industry. And this is one of the points that I might want to hint on, that yes, we do listen to the industry, but we shouldn't always listen to the industry, because industry also has short-term requirements. And if we do research that is only short-term, then it won't be long before we run out of ideas that industry will be able to use in the future. And there is a number also of international collaborators across the globe. These are universities, top-tier universities that we have collaboration agreements with. So enough of the promotion. Let me come to AI, and this is just to focus. Well, let me use the laser pointer here. I'm not. I don't intend to discuss a definition of AI. This is just for use, informational use. But what I do want to use this slide for is to use this figure over here, because of course AI is a large set, and then within we have machine learning, and then within machine learning there are neural networks and deep neural networks. Some people call this the hard AI, and this is the soft AI or the narrow AI or things like this. But the reason I'm showing this is because I will focus on machine learning actually, and not on every aspect of AI in this talk. Now, of course, yeah, this is where We have to wait for Microsoft. Oops. No. What you don't see is a message that Microsoft PowerPoint does not respond. That's why I said we have to wait.
Okay, we will need to probably save the presentation on the desktop.
Maybe that's the problem. Yeah, you can keep it anyway, because if people want to take a look at the slides after the presentation, it's good to have it. Is it this one? Close. Okay, let's hope that it's better now. Okay, so of course you know that AI is not new. It started back in the 50s, and in fact, some people say that it was Alan Turing that was the first one that planted the seed of AI. This is just an evolution of it. I just wanted to draw your attention a little bit to this period over here, between 1970 and 1990. Which is very, very aptly, I think, called the AI winter, because nothing was happening, or at least it seemed that nothing was happening in AI. But why was that? Any suggestions? Yes?
Maybe because there was the Cold War, and each country didn't want to publicize the results, thinking that the other country may. Because we put people in the moon, there's no chance that there wasn't some computer development happening behind the scenes.
Computer development was happening, but if you go in particular in AI, this may be one of the reasons, perhaps, I don't know, but I think that
But then it starts computational problems with data.
that was another.
More because you have
Indeed.
question,
Indeed.
but also with the data, so
That's also another reason. I think that some kind of consensus has been reached that this was an AI winter because AI promised too much before the 70s, and it didn't deliver. If you remember, automatic translation was a promise of AI even in the early 80s. It didn't work. They used the well-known experiment of translating actually, I think it was a military manual from Russian to English, and then translating it back from English to Russian, and the result was something that was relevant to vodka. So it wasn't that successful at the time. And then, of course, it came back in the 90s. I'm not suggesting that we will live yet another AI winter, but we should be cautious of when the technology promises too much and then it doesn't deliver. There is this long period. Actually, it was 20 years. It's worthwhile, right? It's considerable. So just keep that in mind. We'll come back to this possibly later. Now, 3 ways in which AI, machine learning, and cybersecurity relate. I've already covered this in the agenda. It is used to improve defensive cybersecurity, so for our defenses, but it can also be used, and it has been used, to improve the offensive cybersecurity, so improving the attacker's capabilities. And then the other way around, cybersecurity is used to defend AI systems from cyber attacks. So let's start with the first one.
Sorry.
Yes?
Can we first case when AI is object for attacks?
You mean yes, well, actually, this is the last one. This is the third. This is the third. Are we having another crash? No. No. Okay. Oops. No, that went too much. So these are some use cases. This is not exhaustive. But there are some use cases of using AI for defensive cybersecurity. Of course, the first thing that usually comes to mind, or at least comes to my mind, because I receive every week dozens of papers applying machine learning for intrusion detection. 99% of them are rejected. And I'll tell you why. But this is the most well-known application. The main reason is that when you test these things in the laboratory, you get accuracy rates of 99%, 98%, nothing less than 97%. But if you try those into a real-world experiment, you seldom get anything above 60%. Simple as that. And there are many reasons for this, of course. This is one of the reasons why, if you look at commercial products for intrusion detection, you will not find many using artificial intelligence. Actually, from the most well-used ones, I think it is only the what was called BRO a few years ago. Now the name has changed, of course, that is using some form of artificial intelligence, but not alone. Actually, it is using statistics, and then there is one component that complements that by using machine learning. But anyway, then an extension, detection of malicious objects, for example, infected PDFs or phishing websites and so on. Defenses against denial of service attacks. This is another also thing that needs to be pointed out, that many people design defenses against particular types of attacks. This is not very helpful because, of course, a system is not facing only one type of attack, it's facing many types of attacks, and therefore designing a defense which is good for only one type of attack doesn't help much, particularly because if you complement that with other solutions, usually the result is that the overall efficiency of the system of the defense system is degraded. Then detection of anomalous or malicious activities. This is actually a subset of intrusion detection. Support for digital forensics, identification of fake and compromised accounts in the online social networks. Same for employee accounts. Threat intelligence, actually, this is a very successful application of machine learning, particularly when it comes to leveraging machine learning for understanding, for acquiring, processing, and understanding unstructured information about threat intelligence, like, for example, from online social networks, right? For example, but other sources as well. Then decision support systems and recommenders for SOCs, for sets, and all the other acronyms there. For authentication, extensively used for context-based authentication and also for biometrics, even though, again, there we do know of several biometrics attacks, several attacks against biometric systems that use machine learning. And finally, for vulnerability detection. Lately, there are some applications of machine learning for doing cryptanalysis of cryptographic algorithms. Actually, of course, you don't use machine learning for actually doing the cryptanalysis, but for guiding the process of cryptanalyzing in a more efficient way. Now, so this is a wide range of applications, right? But just a few challenges to close this chapter of machine learning in defensive cybersecurity. We will come back to the intrusion detection issue later on. So we do have high precision requirements in many cybersecurity applications. One example of this is to have very low false positive rates in detection. And this is one of the biggest problems we have in intrusion detection, high false positive rates. Then, to be fair, when you try to assess the performance of a machine learning-based intrusion detection system or anomaly-based system, to compare it against traditional, let's say, ways of detecting anomalies, this might not be absolutely fair. using the usual metrics of accuracy, of false positives, of false negatives, and so on and so forth. The reason being that usually the machine learning system is part of an overall system. It's part of a bigger system. And therefore, what should be measured is the performance of the overall system rather than just the machine learning component within the system. And that means that we might need to come up with different metrics. Okay, and I already mentioned the last challenge, that in real world conditions, unfortunately, machine learning based IDSs do not really perform very well. Then, next point on offensive cybersecurity. Well, there are bad guys as well. And unfortunately, as every technology can be used for a good purpose, this technology can be used for a bad purpose as well. So we do have several publications in the literature, and I'm absolutely sure that there are many more in the dark literature of how to leverage machine learning to improve the attacker's capability. And in a nutshell, what ML can be used for is to make the cyber attacks more effective, more targeted, cheaper, faster, more autonomous, and more difficult to attribute, and more interactive. Particular emphasis has been put lately on reinforcement learning. This is being used extensively for improving attack capabilities. And there are some examples of use cases. Usage of AI for evading authentication controls. This is a very trivial application to fool CAPTCHA tests. This is why actually CAPTCHA tests have been trying to evolve so as to avoid this kind of situation. Autonomous and automatic movement in cyber attacks. In fact, one of our PhD students has worked on using reinforcement learning for improving attack capabilities against swarms of drones, autonomous drones. Enhanced social engineering, of course, and identity theft, then massive spear phishing attacks, but highly targeted, and interactive and scalable social engineering attacks. All these are available in the literature. This is just one, I would say, crude classification. And the PhD student that I just mentioned to you, actually in her thesis, has come up with a modified cyber kill chain to represent the use of AI in the different phases of the cyber kill chain. I will not go through the details of this picture here, but what you can see is that in all phases of the cyber kill chain, this is not the industrial control systems cyber kill chain, it's the, let's say, simple cyber kill chain. In every one of the stages or the phases, there is a component that can be made more efficient or can be supported by AI. And as I said, the details are there, and of course the reference is there if you want to go through it. Okay, so now this is how machine learning or AI. Again. Something funny happens when I use the laser pointer and then I try to advance the slide. Okay. Well, it needed the master. So, yes. Okay. So the next chapter then is cybersecurity for AI, right? Now, this is one of the mandates of the European Union, among others, about the use of AI. That AI systems must be trustworthy. What does that really mean? Well, if you look at this figure here, trustworthy AI means that it has to be reliable, it has to be resilient, and we did touch upon the concept of resilience. I will come back to that, hopefully. I will remember to come back to that before the end of the talk today. And it has to be responsible. So obviously, the interest here is under resilience, and under resilience, the three attributes are to be safe, to be secure, and to be private. And again, I will not talk, of course, about privacy, but it's about safety and about security, and I would say more about security. So safe, what does it mean? It means doing no harm to living beings or the environment, and Peter covered aspects of this very well in his talk, by the way. Secure, well, it means that it has to be resilient with respect to the CIA triad, confidentiality, integrity, availability, to malicious activities and adversarial attacks. By the way, this is just a slight deviation. If we talk about critical systems, which usually are industrial control systems, the CIA triad is not enough. We need to extend the model beyond confidentiality, integrity, and availability. But as I said, this is a side note. And just to clarify things, because there are many that confuse the terms risk, attack, vulnerability, and so on. Attack is the purposeful manipulation of an AI system with the end goal of causing it to malfunction in some way. And later on, we will see some of these possible malfunctions. Now, what can happen? I guess, do you know this example? No, but you can imagine. This, obviously, it's a cat, right? Fine. And when it was, the image was subjected to one of the well-known ML toolboxes, right? The answer was with an 88% confidence that this is indeed a tabby cat, right? Do you think that this is any different? Anyone that doesn't believe that this is a tabby cat? Well, yeah, one of my students once said, yeah, it's a dog. Yeah, but this was only fun. Well, unfortunately, the toolbox wouldn't agree with you. The result was that this is with a 99% confidence that it is guacamole. So what has happened? Well, obviously what has happened is what we call an adversarial perturbation between the two, right? So the original image was perturbed in a specific way that resulted in an image which is imperceivably similar to the original one, to the human eye, but it fooled the machine learning system. By the way, this is where the example comes from. It's one of the important papers in the literature about this by Adi Shamir and colleagues. Now, is this really interesting, or is it just Adi Shamir playing around with the math of images? Well, actually, what you see on the left side here, this is the cumulative number of papers that have appeared in the literature about adversarial examples in the past years. So you can see that the interest is really, really very high. But remember this when we discuss a little bit later about the feasibility and the realism of such attacks. Obviously, academia, we tend to create problems and then to solve them, right? This is good for writing papers, but the real world may be a little bit different. But it does show that there is a trend in this research direction, right? And what you see on the right-hand side is a classification of, well, not exactly the same set of publications, but a different one, perhaps, on what these adversarial examples were about. And the majority here happen to be about visual recognition. This is, again, normal because image processing is one of the flourishing areas of application of ML, but spam filtering and intrusion detection were not low. And of course, there is this multi-purpose category which has everything in there, or any other business, whatever you prefer. Now, if we just take it a little bit further, any ML system is practically a system that can be abstractly represented by an input, by a processing unit, and by the output. So attacks of this kind can be launched against the input part, or they can be launched against the processing part of it. Of course, they can be launched against the output part as well, but this is not really interesting because this could happen in any type of system. So if we just discuss a little bit about those attacks against the input part of the system, there is a classification which I find quite useful. As you can see, this goes along two axes. So one axis is the perceivability to the human of the attack. So up here we have perceivable attacks. We can identify visually that something is wrong here, but here we cannot. And on the other hand, we have digital attacks versus physical attacks. And there are several examples here. Some of them are quite inspiring, I would say. But again, I have to wait. It's coming. I hope. Maybe I shouldn't be using the laser pointer. Yeah, it came up. Okay, good. So this is a visible attack, and maybe this is something worth looking at, Peter. I don't know whether you can see it, but this is a stop sign, and somebody had stuck stickers on selected places, and then this was classified as green light. So this is a hazard, like the ones that you said, cyber hazard. Maybe,
Yes,
maybe.
pointer.
Yeah, okay. Yes. Yes. Yeah, over here. But of course, it won't be visible in for the online ones, but it doesn't. Yeah. But okay. So this is one case. Does it go?
What was the classified at the same time?
Green light. That can be a bit, catastrophic, maybe. Okay, and then there are other examples of this classification, but it still refuses to continue.
Every time I see the laser pointer, my heart like skips a bit.
Okay, yes.
I think it's gonna crash.
We should stop it. Yes. Okay. No. Did it come up? It did. Okay. Well, this is an invisible attack because it's only adding noise to the original image. You cannot perceive that something has changed, but the panda has become a monkey. And then other examples of physical attacks. Well, of course, again, the stop sign, the turtle that has been painted, that has been classified as a rifle. Yes, and so on and so forth. And finally, this one here, which is a digital attack, and definitely this cannot be Alice as wrongly classified. So just some examples of input attacks. Then, of course, we can go into the processing unit, and here what we have, one can attack the data set, one can attack the algorithm, or one can attack the model. And a proposed classification here by a group of people at Edinburgh, Napier University, that we have collaboration with, is this. So for those of you in the room, the focus is, of course, here. So we speak about poisoning attacks and evasion attacks. The former pertain to the training phase, the latter pertain to the testing phase, and this is how all this can work. And finally, this is another interesting attack again, or the result of the attack. And the same group in the same publication have come up with a classification of attacks against machine learning systems. They looked at quite a large body of literature and came up with this proposal that breaks down the attacks into the preparation phase and the manifestation phase. And here you can see that the the taxonomy or the ontology identifies the knowledge of the attacker, the algorithm, how it operates, whether game theory is being used or not. Yes, game theory has been used to design such attacks. The specificity of the attack, whether it is an indiscriminate one or a targeted one, and then the attack type, and finally operating the attack mode, whether it requires collusion or not collusion. As I said, shouldn't go into detail for that. And again, this is something that I will very quickly pass, because these are different attacker capabilities and there are different attacker goals. I'm only using those to show you this slide, because one might wonder, is it so easy to launch an attack, to design and launch an attack like that against a machine learning system? Well, it turns out that it's not that easy. It may be in several cases, but if you look at the capability of the attacker, well, of course, if you have a white box attack where we assume that the attacker knows practically everything, he or she knows the algorithm, knows the model, knows the everything, right? Then, of course, it's relatively easy to launch an attack like that, particularly if the attacker just wants to reduce the confidence in the classification, which is an easy thing to do. But as the complexity increases towards more targeted attacks and the capabilities of the attacker decrease, then you can see, of course, this is not linear. No one knows how exactly this could go, but the trend is that the difficulty increases with decreasing capability of the attacker and the increasing complexity of the attack. Now, moving on to one of my favorite parts of it, which is the use of machine learning for network intrusion detection systems. It also applies to host-based intrusion detection systems, but this particular figure has been taken from a paper that was discussing needs. And again, the question here is this. As I said, there are many papers that demonstrate how attacks against network intrusion detection systems can be designed. But until very recently, as you can see, this is a publication in 2022, and there is another one which has not yet been published, not by the same authors, but I have happened to review for a conference, and I know that it will be accepted. So I can, even though I don't know the authors, because it was a double-blind reviewing system, but still I will give you some of the result there. So no one had looked upon, to answer the question, fine, but is it feasible to design and launch an attack like this against a NIDS or a HIDS? And furthermore, is it realistic? So to cut a long story short, it's neither feasible in many cases nor realistic. And there is a very good reason for that. When it comes to images, there are practically no constraints within the structure of an image. So you can design an attack that will change the image in any way without violating any constraints. But if you try to launch an attack against an intrusion detection system where the data are very much structured, and in the feature space you have constraints between the different features. An example is that the payload cannot be larger than something, right? Just a very simple example. So this would mean that if you wanted to launch an attack against the machine learning system looking at this data, this would undergo the same constraints as the data themselves. And this has not been the case. So in fact, if you look at this column over here, which is the third from right, for those of you online, you will see.
I think we can use the laser pointer now.
No. So I'm pointing at the third column from the right. You will see that all these are publications about adversarial attacks against machine learning based NIDS. Right? Constraints have not been verified in most of them, which means that. So all this doesn't apply to the real world. Very few of these described attacks can apply to the real world. Okay, but there is something else as well, and coming back to the AI winter, right? Well, we tend to use AI, machine learning these days for almost everything, believing that it's better than what we've been doing up till now. But it turns out that this is not always the case. This is a paper that appeared in the last ESORIX last September. The authors did a very simple thing. Actually, the title of the paper is simple, but this is an acronym. I won't bother you with what it is. But they asked the following question. Let's look at the literature using machine learning-based intrusion detection for industrial control systems. And let's see what results we would be getting if we applied simple statistical threshold algorithms on the same data sets. Imagine what? Oh, the statistics one. Yes. The statistics one. In most of the cases. So, well, that's why I'm asking, is it always better? No. I could also argue, everyone today uses blockchain. Do we have to use blockchain? Is it always the best solution? Well, I don't really think so. These are nice technologies, but we should be careful with when we use them because there might be something better.
The CNSP data is not useful for any.
Exactly. Absolutely. Absolutely. Again, for academia, perfect. You write papers. We write papers, right? Yeah. But okay. Final. Is there anything we can do? Yes, of course. And there is a lot of literature on defensive strategies. But again, I will come back to this point that all these strategies are specific for specific attacks. And it's no good doing something that will protect a system against a specific attack, and then it will leave it undefended for all kinds of other attacks. And as I said, in most cases, when you combine defensive strategies like this, the end result is not better than if you had nothing there or if you had a few of them there. So, any way to go forward? Well, I will just only give you one point here because I have to conclude. First of all, machine learning is only one part of a system. And I believe that we should be looking at the system. That's point number one, not just parts of it. And if we do that, then we need to have a holistic approach that will include people, technology. Technology is ML, but other technologies as well, right? And processes. And one way of doing it, of course, is by using the NIST cybersecurity framework. I happen to believe this is a good way of addressing these problems. Yeah. And then, looking at the time, unfortunately, machine learning works by learning patterns. We rely on data, but they are liable to break easily. The third bullet, because I already commented on the second one, goes to the black box nature. This is the explainability. We know that we can combine explainable AI, which doesn't have good accuracy, with non-explainable AI, which has good accuracy. But putting them together, again, is a challenge, and that doesn't mean that it cannot be attacked. But the major point here is that the attacks that have been made possible, they're not due to weaknesses. It's not a weak design of a system. There are structural issues there that need to be taken care of. In the image classification problem, what happens is that actually a few pixels can be moved below the hyperplane that separates the two regions of decision, and that's it. This is not a weakness. It's a structural problem. Then, is it a threat? Yes, it is. Poor performance in intrusion detection, at least, has been demonstrated, but several of those models that have been proposed are unfeasible or unrealistic. But it doesn't mean that we cannot use and we should not use ML and some of these conclusions to other detection problems, for example, phishing, malware detection, and so on. In fact, the first time I used machine learning for intrusion detection was 30 years ago. We developed a neural network within the context of a European project for what was then called the integrated broadband communication networks. This was the buzzword of the Commission at the time for what we now know was networks. It didn't work for several reasons. But then, of course, we have used it. Also, my team has used it for malware classification. We used it very recently for detecting anomalies in the NMEA protocol. This is a communication protocol, network communication protocol, shipboard for ships. And we found that we shouldn't use it. We reverted to the statistics again, and so on. But there are applications there, right? So when we talk about mission-critical systems, we should be careful enough not to introduce vulnerabilities because of the use of AI in these systems. So what we need to do is to improve our understanding of how the two domains interconnect. This doesn't mean that we need experts that will be experts in both domains. We need experts from both domains to work together, and we are doing that at NTNU, fortunately, and to, of course, leverage this understanding to develop methods and tools so that we can efficiently address all these challenges. So it's all about collaboration. Thank you very much.
One small question, and it's more of a comment, not a
Yeah, sure.
question. But how much can we use and depends on AI systems to defend our structures? Because AI will need to feed some data. That data already exists. Nobody knew a DDoS attack before it existed. Nobody knew an anonymous attack before it existed.
Sure.
All those stuff. So we cannot be too dependent on AI because it cannot innovate. AI cannot innovate. It cannot find a solution to something brand new, to something that hasn't been introduced to it, so it can learn, right?
Well, actually, machine learning claims, and it's a valid claim, that it can identify unknown attacks. Right? So if we have an intrusion detection system, ML-based, that has been trained on a set of attacks, right? Then, at least in the laboratory, we can demonstrate that it can also detect an attack that it has not seen before. But mind you, it's only in the laboratory.
To detect the anomaly of the system.
It can detect an attack. Well, it cannot tell you that it is an attack, but it can tell you that it is an anomaly, and therefore something, exactly.
Yes,
Thank you very much for your presentation. It was extremely interesting talk. My question is related to traditional security protection based on defense in depth.
Yes.
What your opinion? Is it possible to build protection system based on AI defense in depth? I mean, AI has a few specialties.
Yeah.
Similar in this classical.
Yes. Yeah, you can say this, but yeah, I think, well, it depends on the layer, and we've seen applications of different machine learning and AI technology at different layers of defense in depth. But I'm not sure that this can be applied to all the layers of a defense in depth model. But just inspired by your question, what I think is also important is this. let's say 20 years ago, our security paradigm was that we should keep our systems secure by protecting them against the bad guys, right? But then, when communication technologies were integrated with information technologies and the systems opened up, so the computing paradigm changed. Our paradigm changed as well. And the emphasis was not so much on protection. It remained on protection, but there was an additional emphasis on detection. Why was this? Well, because the basic assumption that we could keep our systems relatively well protected and therefore they couldn't be attacked was not valid anymore. And we started assuming that even though we may be well protecting them, like, for example, defense in depth, right? Still, we would be attacked. And therefore, we would need to have procedures in place so that we could detect the attack. But in the past few years, one of the stimuli for what I will say have been the attacks against the Ukraine Oblenergos in 2015 and 2016, right? We now know that we will not only be attacked, but we will be successfully attacked, which means that now there is an additional focus. Not only protect, not only detect, but also respond and recover. So, and this is where brings resilience into the discussion, right? So,
It's real resilience.
yes. So maybe, I don't know whether I answered your question about the defense in depth and the AI, but I did take it as a trigger to comment a little bit
Yes,
further.
my question is based on my experience in safety.
Right,
Yeah.
yes,
Where
of course.
atmosphere is the main
Absolutely.
challenge.
Absolutely, yes, you're absolutely right. And of course, we have borrowed the defense in depth strategy in cybersecurity from safety, right? But there is a fundamental difference. In safety, we assume that there will be hazards, but this will not be coordinated. They will not be coordinated. And this is a fundamental difference with cybersecurity, because the cybersecurity, many people ask, okay, why then don't you just use what we know from safety and port it to cybersecurity? Well, an accident is an accident, but a cyber attack is not something that is at one point in time. It's a coordinated action that possibly is not just one action, but it goes on and on and on, right? Yes. And this changes the model quite significantly. Yeah, Peter, you.
I'm probably okay.
Okay, good. Yeah, okay.
I wanted to make an observation that you mentioned intrusion tolerance.
Yep.
Because intrusion tolerance seems a big deal, at least in my mind. This is tested in cybersecurity. You don't make any assumptions about who, how they're going to attack, what they're going to do, and yet this is successful under certain assumptions, of course. So, but
Have any questions, please? More questions? From
Maybe I
online?
should stop sharing here.
That's okay. Okay, we don't have more questions. Thank you very much.
Okay.
Thank you very much, Professor Katsikos.
Thank you.
We have now coffee break. We have a small shift that comes from morning time. So start at 4 o'clock. Yes, 4 o'clock. After 15 minutes. Yes. 4 o'clock. Yes. 4 o'clock. 2 sessions. Yes. 2 sessions.